Thanks everybody. As mentioned, I'm Stefan. I'm one of the founders of Emesent, stepping in for one of my colleagues, Jeremy. And today I'm going to be presenting on a couple of things on that topic, but also a sneak peek on what we've been doing with terrain following, and also some other work we've been doing in autonomy. So yeah, thanks for listening. So for those of you that are maybe not aware of Emesent and who we are, we're based in Australia and we develop solutions that provide both mapping and autonomy using LiDAR and SLAM. We've been doing this for around 7 or 8 years now commercially, and prior to that we were a part of a research organization in Australia. So we have a full solution stack from data capture through to insights. And we do partner up with third-party vendors to provide some of those insights as well. And our solution is a combination of hardware and software, and at the very core of what we do is SLAM, and then we use SLAM for both autonomy and for producing maps. And I'll just say, usually at events like INTERGEO, we focus more on the mapping side of things, because obviously, usually the audience here is interested in mapping. Our autonomy is very widely used around the world in mining applications and other applications where you need to capture data in challenging environments, and autonomy really makes sense and helps. But I do believe there are applications in the AEC space where autonomy definitely can help, and that's why this time we decided we'd present a little bit about our autonomy capabilities, some features we've already released and some new things that we're working on. And part of the idea is to actually get feedback from the audience. I'd like to hear from you. Could this be useful? What else could we develop to help capture data in sort of challenging environments where terrain following could be useful? So as you can see, our core product is Hovermap. So this is the hardware and software device that can be mounted on various things. Here you see it mounted onto a drone. And as you'll see, when it's on a drone, it can provide full autonomy, flying beyond line of sight, beyond communication range, without GPS in very challenging environments. But it's always been developed as a plug-and-play system that can be used in different modes. So we can put it on ground robots, like the Spot from Boston Dynamics, provide autonomy and mapping on those platforms, and a few other ground platforms. But you can also just use it as a traditional SLAM-based scanner. So you can carry it by hand, backpack, put it on a vehicle. So it's a very versatile system. And we can combine both SLAM and GPS. So you can see into those images, we have RTK receivers, so we can combine RTK and SLAM when RTK GPS is available. When it's mounted on a drone and you're using the autonomy mode, we've got a few different ways that you can interact with the autonomy. One mode is what we call pilot assist. So it assumes you can see the drone, your line of sight, you're using the controls, but Hovermap is keeping the drone safe for you, so it's doing collision avoidance with the LiDAR data in real time, and also doing position and velocity control. So if you're flying underneath a bridge and you lose GPS, you can take your hands off the sticks and the drone will keep very safe and stable. Obviously, if you're flying underground in a mine or a tunnel, you can still do that line of sight. And this is useful for doing asset inspection, like mapping towers and bridges, etc. You want to see the drone and use the sticks to position in a position to take an image. If you're going, for example, underground in a mine and you want to go beyond line of sight, beyond communication range, then we have autonomous waypoint mode. So when you're using the system, you just operate it off a tablet. We stream a live point cloud to the tablet, and you use that to set waypoints. And those waypoints can be beyond line of sight, outside the existing extents of the map, and our system will then autonomously navigate to those waypoints, returning to home autonomously, etc. So two different ways of using it, and both very useful. These both do require, obviously, human interaction. So you're setting waypoints or you're using the stick. So we've had a lot of sort of requests from customers, how could we make this simpler to avoid needing to use waypoints. So what we've developed and now commercialized is autonomous exploration. So in this mode, you're not setting waypoints, you're just letting the system explore and find places that it hasn't seen before, and making it much easier to operate. So this is actually a video from around 2020, so we've been doing this for a long time. This was a part of a contest we were involved in, organized by DARPA around 5 years ago. And we had autonomous exploration operating on the system back then. And as you can see, it's capable of navigating very tight spaces, avoiding obstacles, and exploring an internal space without any input from a human, and obviously producing very detailed point clouds as well. So over the last couple of years, we've gone ahead and commercialized this, and so at the beginning of the year, we launched our commercial version of autonomous exploration. The way you interact with the system is by setting a bounding box. On the tablet, you define an area or volume that you want to be mapped or explored, and then you launch the system, and then it's hands off. So in this case, we're in an underground mine. There's a combination of underground chambers that have been mined out, and the mine operators don't know exactly how big they are, sort of what their shape and size is, so they've generated a bounding box and they've let the system loose, and now it's exploring underground using the LiDAR to do collision avoidance and navigation. And as you can see, it's a very harsh environment. Obviously underground mines, things are changing all the time. There's a lot of challenges like dust that can be kicked up by the drone. You can often have wire hanging down from the ceiling after they've blasted. There's things that can hang down and obviously be obstacles for the drone. So the system has to handle all of that in real time, and it's using the LiDAR data to detect these obstacles, look for areas that it hasn't yet explored, and then go and map and explore those areas. It's obviously maintaining awareness of its remaining battery time, so it'll make sure that it can reach back to the start point autonomously, so do smart return to home. It detects areas that are too dusty and it will avoid those areas, and as you can see, it got into a dusty area, it then went off, explored another area and came back once the dust had settled, and now it's gone through into a series of chambers that have been mined out and were totally inaccessible any other way. This is beyond line of sight, beyond communication range. The system just disappears, this time for about 15 minutes, and eventually comes back with useful data. And this is the kind of data that's captured. So this is from a different flight, but in a similar environment. And you can see the kind of environments that can now be captured are very complex, unstructured. You might not know anything about that environment. Particularly useful if you haven't been there before, so you don't know the size and shape of an environment. Difficult to set waypoints because you don't know where to place those waypoints. So you can now explore these areas with a very simple user interface and obviously robust autonomy. So that's autonomy for underground use cases, and obviously very important to have autonomy there, but there are also use cases above ground where real-time collision avoidance and autonomy is useful and can make sense, and this is what we started exploring recently after getting feedback from customers. And one of those sort of typical environments or scenarios is mountainous terrain or uneven terrain, terrain that might be changing over time. So if you think of a mining environment, they're obviously changing the terrain. So if you're relying on a terrain map to set your flight paths, that might be out of date. So if you've got a situation where it's very uneven, you don't have terrain maps, or there might be out-of-date terrain maps, situations where you might not receive GPS or get partial GPS. For example, if you're going into a very deep pit, you might start losing GPS. So traditional GPS-based navigation can be a challenge. And also usually one of the requirements when you're doing this kind of above-ground mapping is to generate even point density, and that means you need to try and keep an even height above the ground because that determines your point density. And if you're relying on SLAM for mapping and for navigation, obviously SLAM needs to see features on the ground. So if you end up flying too high, you're not going to have a valid SLAM solution. So it makes sense to use the autonomy to ensure that you're getting valid SLAM points on the ground. So with that in mind, what we've gone ahead and done is generate a prototype terrain following system, and it can do all of this without using GPS. So one way of interacting with the system is if you've got GPS and you've got a Google Earth image, you can draw a polygon of the area that you want to have mapped. Then our system will generate the flight lines, either a lawnmower pattern or a spiral, pros and cons of different ones. And then it'll launch the mission. If you don't have GPS, you can also just designate a polygon that's currently positioned relative to the start location. So you don't have to have GPS to do this. And then once you launch the system, it goes ahead and generates flight lines and flies those flight lines while navigating, following the terrain. So here you can see we're flying in a quarry. This is on a DJI M350 with Hovermap attached, flying up to 10 meters per second to navigate this obviously pretty steep sides to this quarry, so it would be a challenge to manually plot a flight path that can give you even point density over this. So as it's flying, we're using the LiDAR data to do the terrain following. We're also live streaming a point cloud to the user interface, so you can check your coverage, and you can interact with that mission as it's going. So you can add tasks or waypoints. And then this is the kind of data that we've generated from that flight. As you can see, the flight paths have followed the contours of the terrain very well, keeping an even distance off the ground. And then from our LiDAR data, we can also project color data onto that from a GoPro that we have on board. So we get colorized point clouds with very good point density or even point density in these challenging environments. This is another example of a quarry. These are the flight lines that were planned by our system and flown. And when you look top down, it looks like a pretty easy environment. But when you look at it from the side perspective, you realize how challenging some of these quarries can be. And obviously to plan a flight path like this, just using sort of standard techniques would be very challenging, especially if you want to maintain that even point density. And that's just from another perspective. This is another use case or another example where we're now flying terrain following over a mountainous environment. So this could be if you're trying to map a power line or a pipeline that's going over very rugged terrain, mountainous environment, and you don't have up-to-date terrain maps. You could use this autonomy system to follow the terrain. One of the parameters we allow you to set is height above ground. So you can set the height above ground. In this case, I think we're flying around 30 meters, and in some cases that meant we were getting close to the treetops, but our system could navigate the tops of those trees. So again, that was on a M350, so we managed to fly over 1 kilometer out and back again, triggered the low battery return to home using our autonomous return to home, following the terrain. And because we've managed to follow the terrain in this environment, it makes it much easier to generate digital terrain maps. So getting even point density on the ground and make sure you penetrate through the canopy allows you to generate better DTMs from the data. And then this is another test we've done recently. Now we're really kind of pushing the limits of what we think is possible with real-time SLAM-based navigation above ground. So now we were flying at 100 meter altitude and 10 meters per second over a forested area. So obviously, as you can imagine, for a SLAM-based system to detect features on the ground at that height and speed becomes a real challenge. But we've proved we could do this even at those height and speed, flying out to over 4 kilometers and returning back to base. So the interface we have for this is allowing you to set a range and a bearing and the size of a scan pattern at the end of that path. So you could go out, say, 2 kilometers and then scan a 1 by 1 kilometer area and come back, all without using GPS, and that could be over mountainous terrain as well. Obviously, over those distances, if you're just relying on SLAM, you probably will get some SLAM drift. So by the time we've returned back to base, we were about 1% off in terms of SLAM drift, but it brings the system close enough that a pilot can then see the drone, take back control and bring it down to land. So those are examples of where we're trying to fly above the trees and the terrain, but you might also want to fly very close to the ground. So here's an example where we set an area to map using the spiral pattern, and the flight height was set, I think, to around 3 meters above ground, which means sometimes it was below tree level. And this is what that flight looks like. So this is pretty nerve-wracking to be there in person watching the system flying around in and amongst trees. You can see it's using the LiDAR data to fly in that flight line, avoiding obstacles. Sometimes it'll go around the tree, sometimes it'll fly over them. All depends on I guess what it sees in real time and make those decisions. So this is could be very useful if you need to capture high density data that can be above or below canopy and ensure you get coverage over sort of challenging environments. Even flying through trees, like I said, this is hard to watch sometimes. You don't know where it's going to go next and what it's going to do. And yeah, obviously generating very, very detailed data from a flight like that. And you can see some of the trajectories have gone over the obstacles. Obviously that tree was just too dense to fly through, so it's gone over the top. In other cases, there's smaller trees that it could find its way around, so it's done that. And towards the end, it actually flew in between the branches of some of the trees as well. So I guess the use cases we've talked about, forestry mapping above and below canopy, quarries and open pit mines, especially if they've got steep sides and the terrain is changing. If you're trying to map power lines or long linear assets over mountainous terrain, and doing magnetic surveys. So for doing mag surveys, obviously you want to fly low to the ground, consistent height above the ground. So if you're doing UXO or sort of mine exploration, you could do mag surveys with the system. And then the benefits is obviously you don't need pre-existing terrain maps, and it doesn't matter if the environment's been changing. You can do all of this without using GPS. Very simple to plan the missions because you're just defining a polygon and a height above ground. You end up getting a very consistent point density, and obviously it improves safety because the system is doing collision avoidance and avoiding the terrain as it flies. And then if you're using a SLAM-based system, this ensures you're always getting SLAM features within range, so your SLAM solution will be valid. So yeah, I mean, definitely curious to get your feedback how this could be used, what else we could do to make this easier and more intuitive to operate. So that's sort of part one of the talk, and then in a few minutes I'll just talk about the second part of our workflow. Once you've captured the data, you need to process it. So we have Aura, our software, which does that. We've just released a very big update to that, Aura 2.0. So some of the main features in Aura are related to the way we do georeferencing. So previously we had a workflow in Aura where you could put our retroreflective targets in the environment, and our software Aura would automatically detect them in the cloud, do the constellation matching, and use that for non-rigid georeferencing. So improving SLAM and doing georeferencing. Very effective, but quite painful if you had to put these targets in place. So what we've now released is the ability to use anything in the environment as a GCP target, using our custom GCP feature. So you can basically walk around with the scanner. You don't have to put it on anything. You can keep walking and scanning anything in the environment that you can identify in the point cloud by intensity or shape. You can designate as a GCP. And then in Aura, you can go and either semi-automatically detect high-intensity blobs of points, or use the cursors to very finely select your target and designate those as GCPs. And then we have the ability to either use them as control points, which actually influences the SLAM result, so it's actually impacting the SLAM in a non-rigid way, or you can designate them as checkpoints, so it's not actually influencing the SLAM, but you still get an accuracy report from those checkpoints. And then we generate accuracy points for both the control points and the checkpoints, so you can see what the quality of the result has been. And we also provide this in a spreadsheet of Excel file, so you can interrogate in a lot of detail. We've also updated our licensing management system from a hardware dongle. Now you can do all that on the cloud by using just a software license, so that's making it a lot more flexible for our customers to use our software in many different ways. And a lot of other new features in Aura 2.0, so if you'd like to learn more, come upstairs and visit our booth, and love to hear more about the potential use cases for autonomous terrain following or SLAM-based autonomy. Thank you.